Okay, how we doing? You got something? Anybody want to share their screen and show us what they did?
I can, and we can kind of go over. And the result came out correct. The plot doesn't look quite like the Wikipedia, but I can share.
Okay.
I chose the Beal function. And this is a snippet from the Wikipedia page over the design space from negative 4.5 to 4.5 for X and Y. And it says that the global minimum should come out at X is 3 and Y is 0.5, and that is the result that comes out.
Cool. Sweet. Okay, so one thing that I didn't mention is that sometimes these in Excel you have really limited control over these contour plots, and you might be able to have a little bit more control if you had finer steps in X and Y. You know, if you were doing those every 0.1 or 0.05 or something, you know. So you have a much larger data set there to look at. It might be able to do a little bit more with the contour plot because it really only knows values at the locations that you're computing them. And you can see that those minima down there in the Beal function from the Wikipedia page, you can see that those are kind of thin slivers and things, right? The like the little blue, the blue regions in there are kind of thin. So it's probably having a hard time like getting some of that with the resolution that we're looking at here. And this is one nice thing about going with Python or some other code to visualize these is you can recreate these plots very rapidly and take really fine steps and have a lot more control over the contours. When you actually plot things in Python, for example, you can choose what values you want for the contour lines, how many contour lines you want, you know, in Excel, maybe there's ways to do that. I really honestly don't use Excel very much for contours because of its limited, or, you know, I'm just not very good at it. Maybe it's more capable than I think it is, but anyway, so those are some of the limitations, I guess, with trying to use Excel to do this, but great. Okay. Thank you. Anybody else? What other functions did you choose, and anyone who wants to share?
I can share mine. So I did the egg holder function. So this is what it resulted with here. This one looks like it matches that a bit more. But I just found these different styles within the contour plot section. So I thought it was neat to take a look at these different ones. What I did is I saw that it was plotting these across these ranges. So I did something similar to what we did earlier, where I just took steps of 100 from negative 1000 to 1000, and then typed that function in for the X and Y.
Great.
Yeah.
Cool. Well, it looks pretty representative there.
Yeah. Yeah. So that's what I did.
Okay. So those different plots are just like preset plots that you found in Excel?
Yeah. These different plots were like, if I went to chart style and then went to like insert chart and then all charts surface, and then I found there's these different styles I could do.
Great. Okay. All right. Very nice. Thanks. Anyone else?
So I did the same one as Nolan. I did the egg holder. So I won't show it, but just an interesting note. I was curious whether the optimizer could the GRG whatever's built into Excel, whether it could figure out the minimum, at least the one that's reported on Wikipedia, and I more or less had to hand it the result for it to find it. It kept dropping into local minima, which I thought was
Mhm.
interesting.
Cool. Yeah, we're gonna go over some of that. Good, Ben. Okay, anyone else have something they want to share?
I'll share something really quick. Can you hear me?
Yeah.
So I first did the double blouse function, which looks like this. In order to see kind of this local maxima right here, I had to do the wireframe. It didn't show up very well in the other view. So even if I like did it like this, it's more difficult to see that local maximum, just how they do the shading. And I tried to do the 3-hump camel function, and I had a hard time getting it to work in Excel. So I showed it in, I plotted it in GeoGebra. Are you able to see my screen if I switch over to GeoGebra?
We're still seeing Excel.
No, maybe not. This is what it looks like plotted in GeoGebra, the 3-hump camel function.
Cool.
But I couldn't get it to plot very well at all in Excel. I don't know what issue I was having there.
Mhm. Sweet. GeoGebra. I've never heard of that. What is it? Just a
Yeah, it's just a 3D plotting software. We use it down at Snow College in Calc 3 a little bit to see 3D design spaces more. So you can kind of see the hills and valleys in there a little bit better than Excel can at times. And you can move it around and manipulate it to see it from different angles.
yeah. Oh, that's fantastic. That's what we should be using here, huh?
GeoGebra has a lot of pre-made calculators because it's kind of like a community where people have already created calculators as well that you can, where they have sliders and stuff as well that you can manipulate to slice them.
Huh. Sweet. Okay, well, I'm gonna write that down.
I can drop a link to it in the chat.
Okay. Okay, did everybody get to share that wanted to? So I'm just gonna put a little star here, geogebra.org. Is that right? GeoGebra. Yeah, cool. All right, so hopefully you guys now understand like what these design spaces can look like, how to visualize one, you know, above. If we're trying to look at more dimensions, it's more challenging, obviously. Oh, I'm not sharing my screen, I just realized. There we go. So it's harder to visualize them the more dimensions you have, but you can still get a sense for what they look like if you take a slice through that domain. Okay, so, and another thing, by the way, you could have, a lot of these are just 2-dimensional, you know, X, Y, X, Y, X, Y, X, Y. But let's take this one, for example, Rosenbrock. This can be more dimensions. You can have as many N as you like, it looks like here. And so you can set your higher dimensions to any value you wanted. You know, we could have included more terms in here, or maybe let's go back to the sphere function. That's easy to think about because we actually did it as an example. But, you know, we could include as many terms here as we want, and we could have set, you know, X3 to 5 and X4 to 10 and X5 to whatever, and just held those constants and still looked at a slice through the domain for those values. Does that make sense? We didn't have to set those to 0 to look at a 2-dimensional slice. We could have, they just have to be held constant if we're going to look at a 2-dimensional slice through this domain. So we could have chosen any value that we wanted for those other X parameters out here to take a 2D slice and visualize what the domain looks like at that point in the design space, right? Or at that slice in the design space. And then you can change those upper values, you know, so you could change each of those to a different value to look at different slices through the design space in another dimension. So that's really helpful sometimes, just to try to visualize what's going on, where you have local minima, where your optimization code might be struggling, and so forth. All right, so with this in mind, with these somewhat complex and possibly complex, we a lot of different options of what these design spaces might look like. I would like you guys now to brainstorm for just a minute. How are we going to teach the computer to find the minimum? What are different ways we could teach the computer to solve this? So I'm just going to say ways to solve this. And by solve this, I mean to find the minimum. What are your thoughts? How would we do this?
So here's an idea. What if we've got like a two-dimensional function, we throw out a grid of say 100 points over this two-dimensional function space. We evaluate the objective function, each one of those 100 points, and then we take and based on some threshold, we could slice and say, okay, I want like the 50 or the 20 lowest points. We take those, we draw some kind of bounding box around those points, and then we redistribute 100 points in that space, slice off the lowest 20, redistribute, slice off the lowest 20, and just kind of keep going down, down, down.
Great.
I don't know, that's what came to me just barely.
Okay. That's great. What should we call this? What would you like to name this?
Oh dear.
How about bound and search? How's that?
Yeah. Search and bound.
Search and bound.
I like it.
Okay. Did you guys catch that? So we run this grid of 100 points across this domain. We find the region that has the smallest. We kind of put a box around there and rerun 100 in there, or you can have as many as you want, and then you just kind of narrow down until your solution stops changing. All right. So I'm going to put copyright by Corey 2022. He's going to publish that next.
Yeah, I appreciate it. You'll see a patent to that in a couple of years.
Okay, great. Okay, other thoughts? So one thing, maybe I should point this out that may not be totally obvious right now. We usually, at the outset of a problem, have no idea what our design space looks like. All right. We usually just have a black box. If you come back over to this schematic here, we have a setup where we've got some inputs, we've got some model, and we've got an output. And the reason we're able to visualize this, and this is really important to understand what types of things we might run into, but when we start a problem, when an optimization code starts a problem, it has no idea. This is a black box over here. It has no idea what this design space looks like. And so what we're trying to figure out is what kind of an algorithm could we use to find the minimum inside of this black box, right? So we're kind of cheating by having an idea of what this might look like over here, but we really don't know what it looks like. So how are we going to teach a computer to find the minimum?
I mean, one of the first conditions that you could have that could solve it quickly is check for inflection points. So you could take the derivative of the function first and find out where the derivative is equal to 0. So that would either give you a maximum or a minimum, just to see if there's any inflection points in the function. Obviously, if there's no inflection points, then you'd have to do a different approach, but that would at least give you a good place where you could start a guess. Because
Okay.
like you're saying, it's just a giant black box. So I'm just looking at I don't know how you use ESOM function or the Himmelbas function in Wikipedia.
Yep. So I'm just moving this over so we can see this a little bit easier. There we go.
I would assume if you were to take the derivative of that function, you would come from this design space, you would have 4 locations where the derivative would be equal to 0, where it would come up and then go down.
Okay. So let's, you mentioned some really important words in there. I'm just going to kind of write them down using derivatives. Maybe I'm going to say you call it inflection points. Yeah, let's write that down.
Peaks and
Inflection.
valleys, possibly.
Say that again.
Peaks or valleys.
Peaks or valleys. Okay, inflection points. Okay. So now this would work if we had an analytic. I think what you're saying here is if we had an analytic thing here, right? So if we have something that looks like this and we can analytically take the derivative of that, and there's some points in here, right, that would be of interest to us, right? Okay, so that's an excellent point. So if we were going to solve this analytically, so to speak, then we could start by looking at this equation here, taking the derivative of it, and you can learn a lot about what this design space looks like by taking the derivative of that, right?
But we have to have the equation, like you're saying.
Oh,
so that is
exactly. Yep. Now we can use some of those ideas, though. We're going to learn about. We can use some of those ideas even if we don't have an analytic solution. We can use some of the same ideas. Yeah. Okay. Nolan, you look like you were going to say something.
Yeah, it's not an original idea, but it's like the way genetic algorithms work, where we give it some space to search for a minimum, and then it creates a population of points and then solves the objective function based on at each of those points, and then finds 2 good ones to make as parents, and then it slightly tweaks the inputs that were made for those 2 parents to create a child, and then it does that for every point, and then just creates like the next population run, and then it does that over and over again until like the ones that weren't good get lost, and then the ones that were good continue on, and then that's good for like if we don't know the like an equation, and if we also don't know, it's good for finding global minima, but not necessarily if we want to find specific local minima, is at least my understanding of that.
Yeah, great. So genetic algorithms is kind of an area, and actually, Corey, I would submit that your suggestion here is a form of genetic algorithm. We'll talk about genetic algorithms tomorrow in more detail. But yeah, they're kind of a branch of optimization, and we'll go over that tomorrow. So yes, thanks, Nolan. Okay, any other thoughts here? I have a few to add, but any others that you want to mention? Okay, so in general, there's a few kind of common methods. One of them that I want to mention is called the brute force. And I guess, Corey, yours is kind of a mixture of brute force and genetic algorithm. So
Yeah,
brute force, what's that?
I said more or less, yeah.
Yeah. So brute force is actually what we did in this example here. We basically said, I don't know what the minimum is for this function. And just as a reminder, this was x squared plus y squared. Now we had the equation, and it's a little bit obvious if you're looking at the equation, that the minimum is going to be at 0, 0. But if we didn't have the equation and we just had that in a black box again, and we didn't know what the answer was, well, one way we can find it is to run a whole range of x and y input values and compute them, right? So this is again what I would call brute force method. We just run a whole sweep over this, And we would find, oh, look at that. The lowest value in this sweep is 0 right there, right? So, and that's very simple to code up. You just call this black box, you know, 1,000,000 times, as many times you want. You sweep over all the different combinations of input variables, and you come out with, this is the minimum value that we found in this whole range or the whole domain. You know, one of the challenges with brute force is the resolution then, because, you know, maybe our step size didn't allow us to land right exactly at 0. So that's where Corey's algorithm would be helpful. You know, we could look and say, hey, our minimum is in this region right here. So I'm going to run, you know, another 100 points in this region and pull out the minimum of that or whatnot. So anyway, brute force, that's a, you know, some people kind of write it off as completely useless. And I don't think it's as useless as many people think it is. You know, sometimes the number of calls to a function required for genetic algorithms or gradient based is very large. And so for, you know, you could have run that many calls to that function using the brute force method and learned a lot more about the whole design space than you did by running this optimization code, where you only now know the solutions at very specific locations. So brute force is also really helpful for visualizing the design space, because then you can take slices through it and look at it without, you know, the only reason we can take slices through this is because we actually know the solution at every point in here. So we had to run the brute force method in order to even be able to visualize this design space. Does that make sense? We couldn't have visualized it otherwise. We wouldn't know what it looks like without having the solution at every point in there. And once you have the solution at every point, then finding the minimum is trivial, right? We just have to pull out the minimum value. Okay, so that's a brute force method. Another one that you guys are probably familiar with as engineers is called trial and error. So all of you have done this, I guarantee it, right? You have you had a function. You said, I need this function to be equal to this. You did this a lot on homework, where you knew what the answer was, but you didn't know the combination of inputs to get that answer, right? And so you would say, well, I think this is what the inputs are to get that answer. You'd put it in and it wasn't quite right. Say, oh, I'm not really sure. I'm going to change this one over here a little bit. We get closer and closer, and finally we get the right answer, and we think that we understood the problem, right? So that's called trial and error. And you can use that for optimization. So you can just keep guessing things and say, well, I'm getting a little closer, I'm getting further away. Really, this is a manual thing usually. This is not a computer algorithm type thing. This is a human algorithm type thing where we just keep guessing things to try to find the minimum, right? So that's trial and error. And again, not very efficient at all, especially when you come to computers. There are much better ways of solving it, but this is something that we as humans often use. And then finally, I want to talk about a family of solution methods called gradient based. And Kyler, yours would fall under the gradient based methods here. So gradient based, and that's what we're going to spend the rest of today on, is gradient based methods. Gradient based methods say, well, you know, one way to solve this is, let me come back up. I really like this example here. I'm gonna zoom in and talk again about how would we find the minimum in this region, but pretend like we don't know what it looks like, right? And so this is just a black box. So what we can do is just guess some initial starting point. So we'll just, you know, pass in a number. Maybe we even want to pass in 0, 0, right, as our first guess. We don't know what the answer is. But gradient-based optimization basically says, okay, I'm going to call the function at that point, and then I'm going to call the function at little deviations to this. You know, so I'm going to perturb the x value a little bit. I'm going to perturb the y value a little bit. I'm going to look at the gradient or the slope of the output in that region. And then I'm going to use that information somehow to guess where I should be moving to get a lower value or move towards the optimum. There are many, many different gradient-based methods. The most, the most simple, I guess, or the earliest ones would be considered steepest descent methods. So basically you would take the gradient, you take a perturbation in X and Y here, figure out what direction you need to be walking to go downhill, and you walk downhill from there. And then, so previously we talked about what if we guessed up here and downhill looks like it's this direction. So at first we would walk downhill. And by the way, steepest descent always moves orthogonal to your contour lines here, okay? So we would cross that line. If we were strictly doing a steepest descent, then we would cross these lines orthogonally or at a right angle basically to these lines. That's the direction of steepest descent. And then, and so we, our algorithm would kind of walk in this direction, keep and test points along the way, update the gradient and say, okay, I want to move this direction, take another step, update the gradient and say, okay, now I want to be moving in this direction. And so it takes a while to get there usually. Steepest descent is really good when you're far away from an optimum to get towards an optimum, but as you get closer and closer to an optimum, especially if it's eccentric, this is what we would call an eccentric optimum, where it's really skewed in one dimension. This is not an eccentric optimum. This is a beautiful optimum because anytime we're crossing these at right angles, we are moving directly towards the optimum location here. You can see that no matter where I start here, if I cross this at right angles, if I use steepest descent, I'm always moving directly towards the optimum. But if the function is eccentric, meaning that it's skewed heavily, and I think there was another example, yeah, right here. So for example, this is an eccentric function. So even with the steepest descent, if I start right here, my first few steps, again, are going to be orthogonal. All of my steps are going to be orthogonal to the gradient, or to the contour lines. But you can see that this step in this direction is not necessarily towards the optimum. It's getting there, but eventually this is going to curve in and hit the optimum. Where if my function is not eccentric, then all of my steps are moving directly towards the optimum. Okay, so this is just a family of optimization algorithms called gradient-based, where you look at the solution at a certain location, you look at the gradient around there, and you try to take steps that are going to move you towards the minimum in that design space. Okay, so I would suggest that most optimization algorithms fall into these four categories here. We have genetic algorithms, brute force, trial and error, gradient-based. Now there are possibly some other categories here that I'm not capturing. We are going to spend most of our time today on gradient-based algorithms, and then tomorrow we're going to talk about genetic algorithms. Okay, so those are the two that I have found to be very useful. And again, there are other algorithms out there you can search on the internet. Obviously, Wikipedia has a bunch of different algorithms you can look at, and there are others that are very useful. But we're going to go over these two basic ideas, gradient-based and genetic, because I think they're pretty important.